The solar system is a single gravitationally bound family, centered on one ordinary yellow star that holds an astonishing 99.86% of all its mass. Around that star move 8 planets, at least 5 recognized dwarf planets, hundreds of moons, and vast reservoirs of small icy and rocky bodies stretching out toward interstellar space. This chapter sets aside the individual worlds, each has its own chapter to come, and looks instead at the architecture of the whole, the shape and regularity of the system as a quantitative object. 2 great facts organize everything. The first is the overwhelming dominance of the Sun's mass, which makes the motion of every other body to a superb approximation, a simple orbit about the Sun. The second is a startling inversion. Although the Sun holds almost all the mass, it carries almost none of the system's spin. The lion's share of that turning motion lies in the orbits of Jupiter and Saturn, a paradox that any theory of the system's birth must explain. The system is defined as the Sun and everything that orbits it, directly or indirectly, and it came into being about 4.5 billion years ago from the gravitational collapse of part of a giant cloud of gas and dust. We can date that birth with remarkable precision. The oldest solids ever found, millimeter-sized inclusions rich in calcium and aluminium, condensed from the cooling solar nebula and preserved inside ancient meteorites, such as the one that fell at a Lend, yield, by the radioactive decay of their lead isotopes, an age of 4.568 billion years. These tiny grains are the true time zero of the solar system, having formed within the first million years of its history, before the planets themselves had assembled. Everything that followed the sorting of rock from ice, the growth of the planets, the sculpting of the belts, unfolded from that beginning, and the meteorites that still fall to Earth carry, locked in their chemistry, the record of those first few million years. Where, though, does the system end? The question has 2 answers because it has 2 quite different edges. The first is the edge of the Sun's gravitational reach. The vast region within which the Sun's pull dominates that of the galaxy, which extends outward 1 to 2 light-years and encloses the Oort Cloud, a roughly spherical shell of perhaps 100 billion dormant comets lying tens of thousands of times farther from the Sun than the Earth. The second is the edge of the Sun's plasma, the heliopause, where the wind of charged particles streaming outward from the Sun is finally halted and turned back by the pressure of the gas between the stars. These 2 boundaries lie enormously far apart. Measured by its gravity, the system is light years across, measured by its solar wind, only about 120 times the Earth's distance from the Sun, and measured by its planets a mere 30. To confuse these edges, as popular accounts often do, is to mistake the size of the system entirely. That plasma boundary is not a matter of theory alone, for 2 spacecraft have physically crossed it. The Voyager probes, launched in the 1970s, flew past the giant planets and then sailed on outward for decades, and in doing so they mapped the outer structure of the Sun's domain for the first time. Voyager 1 passed through the heliopause and into interstellar space in 2012, at about 122 times the Earth's distance from the Sun. Voyager 2 followed in 2018. Each had earlier crossed an inner shock front where the supersonic solar wind abruptly slows. Voyager 1 crossing was confirmed only after a delay, and briefly disputed because its plasma instrument had failed, so the team inferred the boundary from the vanishing of solar particles, the rise of galactic cosmic rays, and a measured jump in the density of the surrounding gas. The 2 Voyagers remain the only craft ever to have measured this frontier from within, and they found not a wall but a structured, turbulent, wind-blown interface. At the center of it all sits the Sun, a main sequence star of the common yellow type, and its dominance is total. The modern practice of astronomy fixes its properties not as loosely measured quantities, but as exact defining constants, agreed by international convention, so that all subsequent work rests on a fixed and reproducible basis. There is a subtle but important reason for this. Astronomers can measure the product of a body's mass and the gravitational constant far more precisely than they can measure either the mass or the constant on its own, for every orbit reveals that product directly through Kepler's law, whereas the gravitational constant itself is known only to a few parts in 100,000 from delicate laboratory experiments. So the Sun's mass is quoted by convention as an exact standard, and a star said to weigh 2 solar masses is understood to weigh exactly twice that agreed figure. This preference for convention over raw measurement runs through all of modern solar system metrology, and it underlies every number in this chapter. The inventory of what orbits the Sun sorts naturally into a few well-defined populations. The 8 planets fall into 2 families of 4. The inner, terrestrial planets, Mercury, Venus, Earth, and Mars, are small, dense balls of rock and metal with thin atmospheres and few moons. The outer 4 are giants, Jupiter and Saturn, the gas giants made overwhelmingly of hydrogen and helium, and Uranus and Neptune, the ice giants, richer in the heavier compounds of water, ammonia, and methane. The disparity in size is staggering. Jupiter alone outweighs all the other planets combined by more than 2 to 1, and could swallow well over 1,000 Earths. Between the rocky inner worlds and the giants, in the gap between Mars and Jupiter, orbits the main asteroid belt, over 1 million catalogued, bodies larger than a kilometre, and yet, as we shall see, so sparse and lightweight in total that they add up to only a tiny fraction of the Moon. Its largest member, the round dwarf planet Ceres, holds about 1/3 of the belt's entire mass. Beyond Neptune, the system opens into its cold outer reaches. First comes the Kuiper Belt, a flattened disk of icy bodies orbiting roughly 30 to 50 times the Earth's distance from the Sun, the reservoir of the short-period comets, and the home of Pluto, prototype of a whole class of frozen worlds beyond Neptune. Far beyond that, enclosing the entire system in a vast spherical shell tens of thousands of times more distant, lies the hypothesized Oort Cloud, the source of the long-period comets that fall in from every direction of the sky. The recognized dwarf planets number 5 so far, Ceres in the asteroid belt, and Pluto, Eris, Haumea, and Makemake out beyond Neptune, though many more frozen bodies will likely qualify in time. The moons number in the hundreds, their tally climbing with every survey. And filling the spaces between, the comets, meteoroids, and drifting dust complete the census. Everything that is neither planet, nor moon, nor dwarf planet, gathered under the single heading of small bodies. The comets deserve a closer look, for their orbits tie the distant reservoirs to the inner system and record its history. They are sorted by the time they take to circle the Sun. The short-period comets, returning in under 2 centuries, come mostly from the Kuiper Belt and the disk beyond it, among them the Jupiter family comets, whose orbits are herded by Jupiter's gravity. The long-period comets, by contrast, take thousands or even millions of years to return and arrive from every direction on the sky, plunging in from the spherical Oort Cloud, far away. That very even spread of their arrival directions is the principal evidence that the Oort Cloud is a sphere rather than a disk, in telling contrast to the flattened Kuiper Belt that feeds the comets hugging the planet's plane. A comet's heart is a dirty snowball of ice and dust only a few kilometers across. Only when it nears the Sun and its ice is turned to vapor does it blossom into the glowing head and streaming tails that make it, for a few weeks, one of the most spectacular sights in the sky. For most of history, the word planet had no precise meaning, and in 2005 that vagueness came to a head. Astronomers discovered, far beyond Neptune, a frozen world named Eris that seemed at least as massive as Pluto, forcing a choice. Did the solar system now have 10 planets or more, or should Pluto itself be reconsidered? The International Astronomical Union settled the matter at its 2006 assembly, laying down for the first time a rigorous definition. A planet, it declared, must do 3 things: orbit the Sun, be massive enough that its own gravity has pulled it into a round shape, and have cleared the neighborhood around its orbit of other bodies. An object that meets the first 2 tests but not the third, round, but sharing its zone with many others, is a dwarf planet. Everything else is a small body. By this definition, Pluto, which shares its region with countless comparable icy worlds, was reclassified as a dwarf planet, and the canonical count of the major planets was fixed, once and for all, at 8. The decisive and most debated of those 3 tests is the clearing of the neighborhood, and its meaning is dynamical dominance. A true planet must be massive enough to have swept up, flung out, or herded into resonance every other body sharing its orbital lane, so that it stands alone. This can be made quantitative, and when it is, the result is striking. On any reasonable measure of how effectively a body clears its zone, the 8 planets outrank Ceres, Pluto, and Eris not by a little but by many orders of magnitude. There is a genuine gap, not a smooth continuum. Pluto, far from dominating its region, is locked in a 3-to-2 rhythm with Neptune that governs its every orbit, one small member of a vast trans-Neptunian crowd. Critics note that the definition speaks only of our own Sun, and a minority prefer a purely geophysical test based on roundness alone, which would remit Pluto and promote the larger moons besides. But the official definition endures, and it reflects a real discontinuity. The 8 planets are not merely the 8 largest round bodies, but the few that are at once round and dynamically supreme. The most striking thing about the system's architecture is its sheer orderliness, and that order is the primary fossil evidence that it formed from a spinning, flattened disk. 3 regularities stand out. The planetary orbits are very nearly coplanar, their planes tilted from one another by only a few degrees, so that the whole system is remarkably flat. Every planet travels around the Sun in the same direction, the same sense in which the Sun itself rotates. And the orbits are very nearly circular, so that each planet keeps close to a fixed distance rather than sweeping in and out. The numbers bear this out. Most of the planets have eccentricities of only a few percent and inclinations of a degree or two. The exceptions are telling. Mercury, the smallest and innermost, has the most elongated and most tilted orbit of the 8. And Pluto's orbit, far more eccentric and steeply inclined still, is itself a signature of its origin among the trans-Neptunian bodies rather than among the planets proper. Each of these orbits is fully described by 6 numbers, the classical orbital elements, that fix the size and shape of the ellipse, the tilt and orientation of its plane, and the planet's position along it. To a first approximation, each planet simply traces its own fixed ellipse about the Sun, exactly as Kepler and Newton described. But the real orbits are not frozen. The planets tug gently on one another, and under those mutual pulls the elements slowly change. The eccentricities and tilts swell and shrink over tens and hundreds of thousands of years, and the ellipses themselves slowly turn in space. More surprisingly, careful computation reveals that the inner solar system is formally chaotic, with a predictability horizon of only a few million years, so that the precise positions of the planets cannot be forecast over hundreds of millions of years, even though the system as a whole is overwhelmingly likely to remain stable for the rest of the Sun's life. The tidy clockwork is real, but it is a living, drifting clockwork, not a rigid mechanism. Woven through the slow drift is a sparser but powerful structure of resonances, places where 2 bodies' orbital periods fall into a ratio of small whole numbers so that they line up again and exchange a coherent gravitational nudge. Resonances can shelter or destroy. The 3-2 resonance with Neptune shields Pluto from ever colliding with it, and defines a whole population of similarly protected bodies. The Trojan asteroids share Jupiter's very orbit 60 degrees ahead of and behind the giant, trapped in stable pockets. But resonances with Jupiter can also clear out the asteroid belt, carving empty lanes, the Kirkwood gaps, by slowly pumping up the eccentricities of any asteroid that strays into them until it is flung away. Each sun-planet pair also has 5 special balance points where a small body can keep pace with the planet. 2 of them are stable, enough to trap Trojans, and others host our spacecraft. The James Webb Space Telescope keeps its station at one such point of the Sun-Earth system. The architecture, in short, is organized not only by smooth spacing, but by a web of resonant relationships, most of them enforced by Jupiter. Return now to the mass, for its concentration is almost beyond intuition. The Sun holds 99.86% of the entire system. Every planet, moon, asteroid, comet, and grain of dust combined makes up the remaining 0.14% The Sun outweighs the Earth by 1/3 times, and within that tiny non-solar remainder, the concentration repeats itself. Jupiter and Saturn together hold about 92% of all planetary mass, Jupiter alone some 70%, add Uranus and Neptune, and the 4 giants account for over 99%, leaving the 4 rocky worlds, the Earth among them, as a rounding error upon a rounding error. The small body reservoirs are lighter still. The entire asteroid belt amounts to only a few percent of the Moon, and the Kuiper Belt to a few percent of the Earth. To a superb approximation, then, the solar system simply is the Sun, orbited by a scattering of debris. This mass dominance has a precise and useful consequence. Because the Sun holds essentially all the mass, the gravitational field throughout the planetary region is, to better than a part in 1,000, just the simple pull of the Sun alone, which is exactly why each planet's path is so faithfully a Keplerian ellipse, and why the planets' tugs on one another are treatable as small corrections. Yet those tugs are not quite nothing. The Sun and planets both orbit their common center of mass, and although that point lies deep within the Sun, the pull of Jupiter shifts it enough that it can sit just outside the Sun's visible surface, so that the Sun itself traces a small circle every 12 years. This tiny reflex wobble is of more than academic interest. Detecting the very same wobble in the light of a distant star, a periodic shift in its spectrum, or a minute's swing in its position on the sky, is precisely how astronomers first found giant planets around other suns, making our own system the calibration case for the search beyond it. Now comes the great inversion. If the mass is hoarded by the Sun, the spin is hoarded by the planets. Despite holding almost all the mass, the Sun carries only a few tenths of 1% of the system's total angular momentum, its turning motion, while the overwhelming majority lies in the slow, wide orbits of the giant planets, Jupiter above all. The reason lies in the arithmetic of angular momentum, which multiplies a body's mass by its speed and by its distance from the center. A planet's modest mass, swung around on an enormous orbit, outweighs the Sun's vast mass turning slowly upon its own small radius. This is the classical angular momentum problem of the system's birth. As the spinning cloud that formed the Sun collapsed, conservation of spin should have whirled the infant Sun up to the very edge of flying apart, yet the Sun turns sedately once a month. The favored resolution is a magnetic break. The young Sun's magnetic field, gripping its own outflowing wind and the surrounding disk, bled its excess spin outward to the material that became the planets. The same accounting explains why one particular plane is the truest frame for the whole system. The angular momentum carried per kilogram grows with the square root of a body's distance, so the far-flung giants dominate the system's total spin, and because Jupiter and Saturn, between them, carry the great bulk of it, the plane defined by that combined spin is essentially their plane. Astronomers call it the invariable plane, the plane through the system's center of mass, at right angles to its total angular momentum vector. Unlike the ecliptic, the plane of the Earth's own orbit, convenient for pointing a telescope but slowly wobbling because it is tied to one small planet, the invariable plane is fixed in space, unchanging, the proper stage on which to study the system's long-term dynamics. And measured against it, the giant planets are revealed to lie almost perfectly flat. Jupiter and Saturn hug this fundamental plane to within a fraction of a degree, exactly as one expects of bodies that formed in, and still trace, the original midplane of the disk from which they were born. Why then the sharp division between the small rocky worlds within and the giants beyond? The answer lies in a single boundary in the young disk, the frost line, the distance from the Sun beyond which it was finally cold enough, only about 150 degrees above absolute zero, for water and other volatile compounds to freeze into ice. Inside that line in the warm inner disk, only metal and rock could condense into solid grains, and so the inner system built small, dense, rocky planets. Outside it, the sudden availability of abundant ice multiplied the solid material many times over, letting massive cores gather quickly and seize great envelopes of hydrogen and helium to become the giants. The frost line lay near the inner edge of today's asteroid belt, and it organizes almost everything this chapter has described: the rocky versus icy divide, the terrestrial versus giant dichotomy, and the belt itself as a zone where the building of a planet was arrested at the very boundary between the two realms. The spacing of the planets, too, shows a curious regularity. Each lies markedly farther from the Sun than the one within it, in a roughly geometric progression. In the 1700s, this pattern was captured in a simple numerical rule, the Titius-Bode relation, which enjoyed two apparent triumphs. It predicted a missing body in the gap between Mars and Jupiter, seemingly vindicated when the dwarf planet Ceres was found there in 1801, and it matched Uranus, discovered in 1781. But then it failed badly. Neptune, found in 1846, orbits far closer than the rule demands. Most astronomers now regard the relation as a numerical coincidence, or at best a loose echo of a real dynamical tendency, that stable, long-lived orbits naturally space themselves in roughly constant ratios, keeping their neighbors clear of the destabilizing grip of resonance. It is a useful mnemonic, but it is no law in the sense of Kepler's or Newton's, and it explains nothing of why the spacing should take the precise values it does. Nor is the present arrangement simply where the planets were born. The most influential modern picture, the Nice model, named for the French city where it was devised, holds that the giant planets first formed in a tighter, more compact huddle, and only later migrated to their present spacing by scattering a vast surrounding disk of icy leftover bodies. As Jupiter drifted inward and Saturn outward, the two crossed a resonance that kicked the outer disk into chaos, flinging icy bodies across the entire system and, in many versions, triggering the great late bombardment that cratered the Moon and the inner planets some 4 billion years ago. This migration naturally explains what a static picture cannot: the resonant trans-Neptunian populations like Pluto's, the capture of Jupiter's Trojan swarms, the stirred-up orbits of the Kuiper Belt, and the very existence of a sculpted, depleted belt rather than a smooth disk. The orderly system we see today is thus the settled aftermath of an early and far more violent rearrangement, its architecture a record of its history as much as a snapshot of its present. To grasp that architecture, one must finally grasp its scale, which spans an almost unimaginable range. The base ruler is the astronomical unit, the Earth-Sun distance, about 150 million kilometers, and the planets march outward in a widening procession. Jupiter at 5 such units, Neptune at 30, the Kuiper Belt to 50, the heliopause near 120, and the Oort Cloud out toward 50,000, close to a full light year, where the Sun's grip at last yields to the galaxy. Shrink the Sun to a ball a meter across, and the Earth becomes a 9mm marble 100 meters away. Neptune orbits 3 kilometers out, and the Oort Cloud would begin some 5,000 kilometers distant, the system revealed as overwhelmingly empty space, punctuated by tiny, widely scattered worlds. Binding it all together is Kepler's ancient law that the square of a planet's period equals the cube of its distance, so that Jupiter takes 12 years to round the Sun, Neptune 165, and a distant comet millions. Even light, the swiftest thing there is, takes hours to cross this quiet, immense, and beautifully ordered domain.